Well, here we go. Summer is gone. Time to go back to school. Except, of course, you're not going to school. School is going to you this time. For this course, Physics 121, though, it's kind of half and half. The lectures will be recorded, and many of you at least will come in and do the labs. Some will choose to do the video alternative. I am not quite sure yet if we're going to have to break up into two groups, but we can take care of all that in emails. One thing I usually do, well, first day of class, people walk in. I usually have 4 piles of handouts sitting there, and I tell people, take one from each pile as you go by. The 4 handouts are, there's a formula sheet that you can use when there's quizzes and exams. There's the syllabus. There's the lab book. Well, I call it the lab book. It's a bunch of sheets with a staple in the corner, but it's the directions for how to do all the lab experiments. And then there's an outline of the lecture notes. Now, as I've already mentioned in an email, this year, they're not all that fond of having us duplicate vast amounts of paper and give it away for free. So you can find all of this stuff in Blackboard, the syllabus, for example. Well, anyhow, that's the syllabus, even though I didn't quite get it in front of the camera. I think there's a thing over there on the side that says syllabus. If there's anything you can't find, just send me an email and I'll give you directions that are a little more specific. Anyhow, I start a course out usually by hitting some high points from the syllabus. I don't want to sit here and read the whole thing. I mean, presumably you know how to read, and we have better things to do with our time. But you should take the time to look through this, not only in my course, but in any of your courses. The syllabus is the rules of the game. If you're going to play the game, you want to know what the rules are. It's a legally binding document. And so in all your courses, look through the syllabus. But to hit a few of the high points, we start out with contact information, which is more important than usual in this, remote instruction situation. The best way to get in touch with me is probably to send an email. You can phone. If I am in my office when you try to phone, I will pick up and answer it. I might be doing something down in the lab, or maybe you want to get hold of me, after hours or something like that. Sometimes I check my email in the evening, but I'm definitely not there going to answer my phone. Anyhow, I check my email several times a day, typically, at least on work days. The textbook. Well, the story with the textbook is that I adopted this particular book because you can get it for free, at least, a PDF. I think it's a PDF, some sort of electronic version of it. You can go to the website that's there. And incidentally, if you go into Blackboard and find the syllabus in there, all of the links should be live. You shouldn't have to type anything. You should be able to just click on that website and go there. But if you want a hard copy, you have to pay what for a textbook is a relatively inexpensive price, to get a printed version. But that's up to you. As far as what you're using the textbook for, all of the homework is in handouts. Okay, so it's not like you have to go to the end of the chapter and do this one and that one and the other one out of the textbook. The textbook is strictly to study from. And if you can get everything from my notes, well, hey, that's great. But you may find that you need a more complete explanation, or just to hear it phrased differently. I don't know as it's the best textbook I've ever seen, but the whole free thing I thought would be good, and I haven't gotten too many complaints yet. I've been using that book for several years now. Aside from the textbook, you need a scientific calculator. It doesn't have to be any elaborate graphing calculator, or just if it's got trig functions and scientific notation. You know, you're talking, typically this is a $10 or $15 calculator we're talking about, although I have seen them at the Dollar Tree. I don't know if a Dollar Tree calculator is going to last the whole semester without breaking. I've never tried, but you might even be able to get out of it for $1 that way. And then you need various other items for the remote aspect of the course. I need to be able to proctor. I mean, I'm going to do as much testing as possible while I've got you there in person that one day of the week. But there's going to be some quizzes, and then everything after Thanksgiving that I need to have a webcam or some. So I got an email today from somebody that asked if they could use their cell phone, that they could do Zoom on their cell phone. I don't care what it is, you know, if it's, as long as it's some sort of a camera where I can see what you're doing as you sit there in front of a computer. And you would need a computer to be able to get into Blackboard, because that's where I'll put the test. So we have an anticipated schedule there. It's the only reason I ever get off schedule. Well, never say never, but it's usually a snow day if I have to revise the schedule. And with everything set up to be done remotely if necessary, we're just going to go right ahead and stick to the schedule if there is a snow day. If you know, if a lab has to be canceled, just watch the video. We'll stay on schedule. So I anticipate being able to stay on the anticipated schedule, unless something comes up and I don't. But so for the grading system, there's a quiz every week. Quizzes are quizzes on the homework. I do not collect homework in the sense of you get a pile of papers and hand it to me. Here's the homework. The very few times that I have done that, it hasn't struck me as particularly satisfactory. I don't care what you can get on a sheet of paper. I care what you've got in your head. So I will quiz you on the homework rather than just asking you to pass it in. The syllabus, well, the first few pages are the stuff that you expect in a syllabus, you know, the grading system and the course description. And there's some stuff in there that they make me put in that I would probably condense down into about half as many words if I had my way. But after all of that stuff, I think it's on page 8, if I remember right. That's where the homework starts. The first 4 homework assignments are right here in the syllabus, after all that other stuff I mentioned. I believe it's page 8. There's a few introductory paragraphs, and then it says section 1, straight line motion. And it says quiz A, and there's a couple questions. And it says quiz B, and there's a couple other questions. And so on. I will pick one of those 5 quizzes at random and print it up on a sheet of paper, or the first quiz might be one that we have to do remotely. I don't have the schedule handy, but whether it's an actual physical piece of paper or some PDF file that you're looking at, the way I make a quiz is I go into the syllabus, I pick one of those 5, block, copy, put a little more space in between so you've got room to write, and that's the quiz. And I change the numbers. So you can't just look at it and say, oh, I remember that one. The answer was 7.7. Yeah, well, it was 7.7 in the homework, but I've changed all the numbers. Maybe the answer is 15.1 now, or 2.16 or something like that. So the way to prepare is, well, let me start with the way not to prepare for the quiz. I have posted solutions to all the homework because it is, I mean, these are not meant to be trivial questions. You have to scratch your head and think about it for a while and look back through your notes, and eventually there will be times when you, no matter what you do, you can't get the right answer. Well, it's a foolish waste of time to sit there for hours once you're just spinning your wheels. I mean, you don't want to give up too soon. It's the struggle that makes you stronger. But after a certain point, when it's pretty clear you're never going to get it yourself, well, I have posted complete line-by-line solutions at the website. That's actually, I think it's a couple of different places in the syllabus here. And actually, I sent you the address in an email also. But one place you can get it is near the top of page 8, where the homework starts. Now, the wrong way to prepare for a quiz is to say, oh, let's see, there's a quiz today. I better look at the homework solutions. So you go in there and let's see, here's the first one. Oh yeah, I see how he did that. And then second quiz, yeah, that kind of makes sense. And the third one, okay, how you do that. And, you know, spend about 8 minutes on the whole thing. And then, well, you see, the problem with that, well, life is not fair. Some people can get away with that because some people just have photographic memories or whatever. But the problem with that is that what I'm trying to develop in this course is a skill, okay? Problem solving skills. And skill comes from practice. I like to make comparisons to learning how to swim or play a musical instrument. You can sit there all day long and watch people swim, okay? And for the first few minutes, that's probably helpful. It's like, oh, let's see, you make your arms go like that, you kick your legs. Yeah, I see how that's done. But if you continue to just sit there and watch people swim over and over again, you can do that for a week. And when I finally throw you in the deep end of the pool, you're going to drown. You need to get in there and start splashing around and get a feel for it and, you know, kind of work your way up to the deep end. And in much the same way, for you to just sit there passively watching me solve problems, well, that's probably a good way to get started. Like, I'll show you how to do a couple of these, but then after that, you got to get your fingers into it and work on it yourself. So maybe you've got a photographic memory. Personally, I do not, but that could get you through the quizzes. Trouble is, the quizzes are, I think it's maybe, yeah, that's right there, 19% of the possible points for the course. So if you think a 19 is a good grade to end up, well, actually, you get the lab points also if you do all the labs. Lab is also around 19%, the same. So if you think a 38 is a good grade to end up with in this course, then by all means, go ahead and do that. But the bulk of the points come from knowing what the heck you're doing, okay? They come from the exams where you have to sit there and figure it out on the spot because it's not just recycled homework. And so you need to work with it. And, you know, the more problems you solve, the better you get at it. And so the right way to do the homework is to sit down with your formula sheet and your calculator and the questions and something to write on and work on it until you're not making any further progress. Take a peek at the answers that I posted to get yourself unstuck if you need to, and then put them aside again and go back to working on it yourself. Okay, don't use the homework solutions as a crutch, but when you're stuck, Or if you just want to see how I did it. Sometimes people get the answer by some correct but circuitous method, and you look at the way I did it, and you're like, oh, I could have done it in 4 lines if I did it that way instead of a page and a half. So that's the right way to use the homework solution. So anyhow, I don't have the date in front of me, but by the date, keep your eye on the schedule on the first page of the syllabus, and on the date when it says quiz 1 will be one of these 5 quizzes with the numbers changed. And the way to prepare for it is to get so that you can do the questions at home without looking at the answers. And then you ought to be able to come to class and do the same thing. And then a week after that will be the second quiz, which will be one of the 5 quizzes listed under section 2, vectors and projectiles, and so on. So typically 1 week apart, there's a quiz, 15, 20 minutes, something like that. Roughly once a month, we'll have an exam, which is not just recycled homework. As I said, you'll have to figure them out on the spot. For many of you, studying for the exam should just be a matter of refreshing your memory. If you've been keeping up with the weekly assignments, maybe you want to look back through your notes because it's been a month since you did some of the stuff. But if things have been going fairly smoothly, then it shouldn't be a huge effort to just get ready for an exam. If things have been not going so smoothly, work more problems. I often tell people it's better to solve 5 different problems once than to solve the same problem 5 times. You can do some end of chapter problems out of a book, or I can even find somewhere else for you to get some more problems to practice on. It's just like learning to play basketball. It's just like learning to play the violin, in that the more you practice, the better you get at it. So weekly quizzes, or typically once a week anyhow, a weekly lab, an exam roughly once a month, a comprehensive final at the end of the course, and then at the end of the semester, I just add up all the points, and that's where your grade comes from. There's no elaborate weighted averaging or anything like that. A point is a point no matter where it comes from. A point from a lab is worth the same as a point on the final exam. And the more points you've accumulated, the larger the smile on your face when you get your grade. Just a couple of other things to mention. Retests. I do not drop any grades. You may have taken some course from somebody else, like, oh, well, I dropped the lowest test or whatever. And I'm not going to get rid of any of your bad grades for you. I give you the opportunity to get rid of your bad grades yourself. So if you take the first quiz and it turns out you are kind of disappointed by your score, you get to take another quiz out of the same assignment within 1 week of the original. For those of you who are coming in to do things face-to-face, one convenient time that you could do the retake is the next time we see each other. The deadline is within a week of the original quiz. So when you come back the next week, that's the last day you can do it. That would be the simplest way to do it, because I can just hand you another quiz out of the back of my notebook there. If you're doing it remotely, we'll have to find some way for you to do it remotely, and we can work that out. But the better of the 2 grades counts. If you get a 6 out of 10 and you take it over, you get a 9, your grade is now a 9, like the 6 never happened. If you take it over and you get a 4, well, at least you get to keep your 6, okay? The only thing you have to lose by well, aside from the time, the only thing you lose by trying is you use up one of your 5 allowed attempts. There are 14 quizzes in the entire course, and you can take a maximum of 5 of them over again. for anybody who isn't just using it to procrastinate, that seems to be plenty. Right now, there's 17 people signed up for the course. Maybe we'll pick up one or two more before all is said and done. But out of a class that size, it's typically 2 or 3 people that max out by the time the course is over. And for everybody else, they end up taking less than 5 re-quizzes. So you also get to take one of the exams over again, one of the 3 exams. We'll do that after the 3rd exam when everybody knows what their worst grade was. The only other thing I'm going to take the time to mention right now is this thing where it says, is this the right physics course for you? I've got that in there because, believe it or not, sometimes people are badly advised. So the best advice is to do your homework and be your own advisor rather than trusting one of us clowns, you know. Look at the schools that you want. If you're a transfer student, look at the schools you want to transfer to and see what they require. You know, everyone's got all that stuff on their websites these days. And whatever they want you to take, that's what you take from us. But typically, anyhow, what a student who would need the 121, 122 sequence would be, first of all, our drafting majors take it. Several of you I know are drafting majors. That's typical. They're usually a significant fraction of the class, although typically less than half of it. As far as transfer curricula, things where you need to know something about physics, but don't need, you know, a major that's not really close to physics. If you're majoring in physics or engineering or some of the other sciences, you need the calculus-based course, okay? Physics 131, that sequence. But like physical therapy, physics, these people need to know something about physics, but not in quite the same, you know, uncompromising way that you would with the 131 sequence. We can cut a few corners here, there, that's good enough. And so, you know, health-related fields like pharmacy and so on, and well, whatever. Now, one thing to keep in mind, especially if your plans are somewhat uncertain, because another thing that's not unusual, aside from being badly advised, another thing that's not unusual is people change their majors. They get halfway through college and say, I don't want to do that, I want to do this. The calculus-based sequence, 131 and so forth, will apply to anything. Whereas there are some other if you take the 121 sequence, there are some majors out, like if you're a drafting major who decides you want to get a BS in engineering and become a licensed engineer, they're going to tell you to take physics over again because you need the calc-based course and all you took was the algebra trig-based course. Okay, so if you're in calculus, if you've got the math, you might want to consider the 131 sequence because it's versatile. You can apply that to anything. But if you're a little more limited in your mathematical background, or you just want a course that doesn't have quite as much stuff stuffed into it, then this course is what's typically taken, like it says here, health-related fields, or also technical fields like drafting. So I always try and cover this in 15 minutes, and it always ends up being 20 or more, and I'm just going to leave this other stuff for you to look at on your own and actually start covering the first section of the course. And I'm going to pause this for a moment while I get the camera aimed differently. Okay, so one of the handouts that I usually give the first day is this packet of notes. And This covers, the course is divided into 14 sections, 14 units, and this has the first 4 in it, which also happens to be what's covered on the first exam. I thought that was sort of a sensible way to do things. Like this handout is stuff on the first exam, this next handout is the stuff on the second exam, and so on. So whether you print it out or not is kind of up to you. It's almost legible on the screen here as I look at it. It's a little on the fuzzy side. It'd be kind of nice if there was a manual focus on this thing. I could make it a little better. But anyhow, we start out with, well, maybe I should give a little background. The first course, Physics 121, and not all of you necessarily need both courses, okay? Some people take 121, some people take 122 by itself, some people take both, some people take 122 first and then come back for 121, but between the two of them, we take kind of an introductory look at least at the physical world. 121 is primarily mechanics and thermal physics, you know, heat and temperature and so on. And then in the spring, Physics 122, the first 2 exams worth of stuff are electricity and magnetism. And then the stuff on the 3rd exam is waves and optics and interference of light and things like that. And then a little bit of atomic and nuclear physics right at the end of the course. So anyhow, we start out with motion along a straight line, which is this. Mechanics is basically the study of motion and forces and things related to that. And the simplest case would be if something's just moving along, you know, one-dimensional motion. Things are more complicated if it's 2-dimensional, and even more complicated than that if it's 3-dimensional. So we'll get to 2 dimensions before very long. But for the moment, just imagine, well, in this example here, I said, what if we had a little wagon, a child with a wagon pulling it down the sidewalk? So motion along a straight line. And maybe the wagon has, you know, the little red wagon used to be a little blue wagon, and there's still some paint puddled up in one end of it that's dripping as you go down the sidewalk. Well, what the dripping paint does for us is leave a record of where the wagon was as a function of time, because the paint's dripping exactly 1 time per second. So first the wagon was here, 1 second later it was there, 1 second after that it was there, and so forth. And you can measure up where all the drips are with a tape measure, and that gives you some data for the wagon's position as a function of time. So terminology that would come up if you're talking about the motion of this little wagon or just about anything else. You might find yourself talking about its velocity. Its velocity means its displacement divided by the time. No, meters divided by seconds equals meters per second, or miles divided by hours gives you miles per hour, okay? We're using the letter X for, if you think of this sidewalk as being like an X-axis, we won't worry about the Y-axis till we get to motion in 2 dimensions, but if you think of this wagon as moving along an X-axis, where is it on the X-axis? Where is it on the number line? That's what the letter X stands for. The little triangle thing next to it is the Greek letter delta. You may have seen that before in some math course. It stands for the amount of change. So where was the wagon in the end? Where was the wagon in the beginning? If you subtract, like if the wagon starts out at x equals 2 and ends up at x equals 5, 5 minus 2, it moved 3 meters, for example. So final delta anything, whether it's change in position, whether it's change in pressure, whether it's change in voltage, Delta anything means subtract final minus initial. So delta x, the change in the wagon's position. Delta t is the corresponding change in time. And the one divided by the other is the average velocity. Well, velocity also includes the direction, okay? Not just how fast is the wagon going, but is it moving toward the right or is it moving toward the left? Things that have directions are called vectors, and we'll get into that in section 2, but I just thought I'd briefly mention it because I might toss the word out now and then this week. And some things like velocity have a direction, other things like temperature do not. The ones that have a direction are called vectors. If you come across the word speed, well, I'm oversimplifying a little bit, but just think of it as meaning the magnitude of the velocity vector. In other words, if you're in a car, maybe you're on the thruway and you're going 70 miles an hour toward the east. That's your velocity. It's a different velocity than the people in the other lane who are going 70 miles an hour toward the west. Speed means the 70 miles per hour. I don't care about the east or the west, okay? Speed is what you read off of a speedometer, and velocity, you have to include the direction along with that. Velocity is the slope of an x versus t graph. Hopefully you've been in some math course where you've encountered the concept of slope before, but maybe not, or maybe it was a while ago and you forgot or something. But if you've got a regular x, y coordinate system like that, and there's some line on this graph, the way you figure out the slope of that line is you pick 2 points. It doesn't matter which two, because a straight line has the same slope everywhere. And how much of a vertical rise is there between the one point and the other? Well, this, how high up is this point minus how high up is that point? You subtract, that's delta y. Similarly, delta x is the horizontal run between those 2 points. How far to the right is this one? How far to the right is that one? Where are they on the x-axis? Subtract that minus that, and it gives you delta x. Rise over run, delta y over delta x. The slope is a number that describes the steepness of the line. A really steep line would have a large number for the slope. A not so steep line would have a smaller number for the slope. A horizontal line has a slope of 0. If the line runs downhill, then the slope is negative. Well, what if instead of labeling the axes in the usual way with x and y, just letters, you arbitrarily use other letters, nothing sacred about x and y. What if instead, get these both on there at once, you labeled the horizontal axis with a T and the vertical axis with the letter X. Position as a function of time. It may look sort of upsetting to see the letter X by that axis when everybody calls this one the X-axis, but the real convention for how you draw graphs doesn't have anything to do with what letter of the alphabet you use. It has to do with what they mean. The independent variable goes on the horizontal axis, and the thing on the vertical axis is supposed to be a function of that. This depends on that. Position is a function of time, not the other way around, okay? If you push the wagon back to the left, it does not make every clock in the universe run backwards. The position of the wagon is a function of the time, not the other way around. So anytime you've got a graph that involves time, whether it's position versus time, or voltage versus time, or temperature versus time, time always goes on the horizontal axis because other things are functions of the time. Time is always the independent variable if time is involved. If it really bothers you seeing the letter X there, well, you can use a P for position if that makes you feel better. But anyhow, if this is X instead of Y, then this would be delta X. You know, if this is X, then this would be delta X. And if this is T, then this would be delta T instead of delta X. And so if you change what letters you're using that way, this becomes delta X over delta T instead of delta Y over delta X. And delta X over delta T is what I just got done saying was the velocity. So the moral of the story is that the velocity is the slope of a graph of position as a function of time. If the graph is steep, that means the thing is going fast. If it's not so steep, it's going slow. If you've got a horizontal line, it's not moving at all. If the line runs downhill, then that's a negative velocity, which means it's going the other way. Okay? If the wagon was going to the left, y final would be smaller than y initial. And when you subtract it, that would make it come out negative. So when something's just moving along a line anyhow, that's how you include the direction with the velocity, is just based on whether it's a positive or a negative number. So every so often I like to stop and have you do something. For one thing, it keeps everyone from falling asleep. Or if you have fallen asleep, at least it wakes you up again pretty soon. In a normal class, I kind of like to circulate around and look over shoulders and see if I can make helpful or possibly annoying suggestions. And that's obviously not going to happen in this remote format, but I'm going to ask you to work on each of these types of problems on your own. And, you know, pause the video. Do the problem as best you can based on what I just went over, and then I'll go over it, which is what I would do in class. After everybody's had a chance to work on it, then I'd go up to the board and write it all out and explain how I did it. And actually, it's a little better in this remote format, because when we do it in class, some people finish a problem in 30 seconds and other people need 10 minutes, and the people who did it in 30 seconds end up waiting for the people who need 10 minutes. But anyhow, as I was droning on about before, physics is something, like any sort of skill, physics is something that you get better at by doing. So don't just sit there and let the recording run and watch me go over it. Try and do it yourself, and then just to make sure you got it right, or maybe to get, and if you can't get it, if you're just hopelessly stuck, well then watch me go over it, then stop the recording and see if you can do it on your own now. Okay, I mean, if you can't get so you can, if you can't get so you can do it on your own, you probably shouldn't go on. You know, you need some sort of help. Anyhow, I'll stop talking. And hopefully now you're restarting the recording after having paused it and worked. This is not a terribly sophisticated example. Calculate the wagons, well, two things. Plot the data, and then I'm not going to mess up that. I'm going to do it on a separate sheet of paper. Well, actually, I've already got it written out here. I might as well save a moment and just lay that in front of the camera. So you need to label the axes, okay, not only with a bunch of numbers, but you should say that this is the position and this is the time, and you should include what units things are measured in also. So like when you do a graph for one of the labs, keep that in mind. Remember to label the axes, or I may give you a sidelong glance, and then you have to listen to me tell you about how you should have labeled your axes. Then you plot up the points. Well, actually, I probably should have had one there also. If I can probably get these both in there at the same time. Yep. T equals 0 when the first drop hit the sidewalk. Now, you know, not T equals 0 as in the beginning of time, but if you've got a stopwatch in your hand, you can push the button and start the clock anytime you want to. So why not picture yourself as starting the clock when that drop dropped? So that's T equals 0. And then since they fall every second, this one would be T equals 1, this one would be T equals 2, this one's T equals 3, and so forth. So this drop here landed at T equals 0. And it's the same sort of thing with position. If you've got a tape measure, you can measure the distances from anywhere you want. Well, let's measure them from here. So this would be X equals 0. And so a dot on the graph goes at T equals 0 and X equals 0. The next dot would be T equals 1, X equals 1.5. So you put the dot on the graph above T equals 1 and to the right of X equals 1.5. And then this is T equals 2, X equals 3, and so on and so on. And you plot all the data that way. And then once it's all plotted up, well, all you actually know for sure is that at these times the wagon was in those places. I suppose you don't have any real evidence that the wagon's position didn't kind of go back and forth in a more complicated way like that. But usually it's a pretty safe assumption that it's the simplest possible function that'll fit the data if you want to fill in where it was at the times in between. Physical phenomena are usually represented by pretty well-behaved functions. And so if all the dots seem to lie along a straight line, yeah, it's probably a straight line. So I got a ruler, drew a line through there. Or actually here I might have freehanded it just because I was being kind of quick and sloppy, but anything like you do for a lab or something, you should draw it with a ruler. Anyhow, that's the graph that it asked for. And then the velocity is the slope of the graph. So to calculate the slope, I just went from the first dot to the last one. The difference in X between here and here is 6 meters. The difference in time between here and here is 4 seconds. And so 1.5 meters per second, that's the velocity of the wagon. Acceleration. The wagon was moving at a constant speed, but many times things aren't doing that. They're speeding up or slowing down, or the rate the velocity is changing is often of interest, and that's called acceleration. Change in velocity over change in time. Now, people like to get these two things confused with each other sometimes because they're both rates. V is the rate that the position is changing. Acceleration is the rate that V is changing. An example of the difference between them. Let's say that you're in a car that's pulling out of a stop sign, and your friend that's driving kind of wants to show off what a peppy car he's got. So, you know, he leaves a patch of rubber and there's smoke and you can smell the rubber, and you get pressed back into your seat and loose objects all go flying toward the back of the car. That's a high rate of acceleration. Meanwhile, overhead, there just happens to be a commercial airliner flying over you, and that airplane is going 600 miles an hour, but it's a constant 600 miles an hour. Now, many of you, I'm sure, have been on a plane at one time or another, and you know that as long as the airplane's keeping a steady velocity, you know, that they're not being tossed around by some turbulence or something like that, it's a lot like being in, you know, on the surface of the earth, sitting in your living room or something like that. Even though you're going 600 miles an hour, it's acceleration that gives you that pressed into your seat kind of feeling. Okay, so let's say that at one particular moment, shortly after the car pulled out of the stop sign, it's going 20 miles an hour, like 1.5 or 2 seconds after it began to move. At that particular instant, it's going 20 miles an hour. And the airplane overhead is going 600 miles an hour. The airplane has a much higher velocity than the car does, but the car has a much higher acceleration. In fact, the acceleration of the airplane is 0, because I said it was going at a constant 600 miles an hour. Acceleration is the rate the velocity is changing. A constant 600 miles an hour, the velocity is not changing. The acceleration of the airplane is 0, whereas the acceleration of the car definitely is not. So the airplane has the higher velocity, the car has the higher acceleration. Or another way of putting it is, if you're sitting in the car, the velocity is how fast the scenery is moving. The acceleration is how fast the needle on the speedometer is moving. Okay, it's the rate that your velocity is changing. Well, just as delta x over delta t would be the slope of a graph of x versus t, delta v over delta t would be the slope of a graph of v versus t. So just as the slope of this graph is the velocity, the slope of this other one, if you draw a velocity graph, that's the acceleration. That's a fact we'll use in lab 1B. The first lab we do is just about the nature of measurement and experimental uncertainty, and it sort of sets the stage for all the labs that come after it. The lab that actually ties in with what I cover in section 1, I called lab 1B. And you're going to determine the acceleration of a falling object. And you do that by getting some data on its velocity as a function of time, and you plot it up on a graph. And the slope of that graph is the acceleration, and that's how you get your answer for that particular lab experiment. Anyhow, another problem for you to think about. I'm trying to remember. I think I made some modifications to the. That's a copy of the notes from last year, and there aren't any significant changes, I don't believe, at least not in section 1. But I think I may have renumbered some of them, unless I'm thinking of what I did for a different course. So, second. Yeah, I happen to be recording this on the day when my website is inaccessible because, well, the story is that the college has decided to upgrade its backup generators. They want to be able to generate enough electricity to run a lot more than just a couple lights here and there if the power goes out. And so right now, as I'm speaking, a couple of weeks before the start of the semester, all of the electricity at the GCC's main campus is turned off so that they can rewire things. And that means I can't get to my website, but I'm pretty sure a couple months ago, I remember making some revisions to this. So you may see some differences in how the examples are numbered. And I think later on in the course, I actually might have changed some of the sample problems and so forth. Anyhow, if you're looking at your copy of the lecture notes and they look a little different than what I've got here, let me know and I'll explain to you the part that I didn't explain to you during this. But I'm pretty sure if I just follow this along, the only thing that's different is what I've called problem number 3 might actually be problem number 5 or 6 or something like that. And I'll make a better effort to have something current in front of me when I make future recordings, because like I said, this is a handout from last year, but I don't think I changed anything too terribly consequential. Anyhow, the next question is for you to calculate the acceleration of the same little wagon that we were just talking about. So pause it. And probably now you're back and you've answered the question yourself, I hope. And it's kind of a trick question. I'll bet a number of you got it wrong. The answer is 0. Now, let me write some of this stuff down. Here's the way to do it wrong. Acceleration equals delta V over delta T. Okay, well, the answer to the previous question, I guess I never did write it down on here. I put it on the other thing over here. It was 1.5. It's on this little yellow sheet here. The answer to number 1, the velocity of the wagon, meters per second. And the time, well, what do we use for the time? From one end of the graph to the other was 4 seconds. And my calculator's way over there, and I don't feel like standing up. But because if I punched it up, it would be the wrong answer anyhow. But it's going to be like point something or other. And delta V is not the same thing as V, okay? The devil is in the details. You can't just go around ignoring parts of the notation. Delta V over delta T. Remember, that means the amount of change. The delta, the triangle, means you have to subtract final minus initial. Well, a straight line has the same slope everywhere. The wagon was going 1 point, you know, if the wagon's velocity was changing, the slope would be changed. Like this would be if the wagon was speeding up, the graph would be getting steeper and steeper and steeper. If you've got a straight line, it has the same slope everywhere, which means the wagon always has the same velocity all the time. So it's going 1.5 meters per second there. It's going 1.5 meters per second there. It's going 1.5 meters per second everywhere. V final is 1.5. V initial is 1.5. Doesn't matter what the number on the bottom is because 0 divided by anything is 0. That's the answer. So without getting into the details of the formula, you can just look at it and say acceleration means the rate the velocity is changing. The velocity is not changing, so the acceleration is 0. So I just stuck a sentence in here to kind of discourage people from scribbling all over the packet of notes, because you might want to, just a second. On Thursday of this week, they're actually going to start letting us back in the building from mid-March until now. I've been in my office twice. I've been inside the building twice since the middle of March. and you had to get special permission, and they're actually going to start letting faculty back in the building again. Anyhow, the only copy of this note packet I had here at home is one that a student had for a short period of time. And every time I've been pausing it, it's where I noticed somewhere else she'd written something on it, and I stop and erase it. Anyhow, getting back to the story here. The next one is one that I thought I would run through to kind of show you something, although feel free to stop it and do it yourself if you want. But this is supposed to be two different pictures, like somebody drops a stone off a bridge or something. So I didn't bother to draw the bridge, but this before picture is just like a microsecond after you released it. Okay, for all practical purposes, it hasn't really started to move yet. You just opened your fingers and let it drop, and at that instant, that's what's being pictured here. Then 2 seconds later, it's dropped down to somewhere below you, and at that particular moment, it's going 19.6 meters per second. And based on that information, what's the acceleration of the thing? So acceleration, change in velocity over the change in time, delta V over delta T. In the end, 19.6 meters per second. In the beginning, its velocity was 0, and the time needed for the change, 2 seconds. Hopefully nobody thinks that's a 5. That's supposed to be an S for seconds. Okay, well, dividing the numbers, 19.6 divided by 2 is equal to 9.8. As for the units, see, units obey the same algebraic rules that numbers and algebraic variables do. So we've got meters per second per second. The change in velocity was in meters per second, and the time's in seconds. Now, when you write units, it's the same convention as when you write numbers, which is that you don't normally leave fractions within fractions. If you solve one of those problems from an elementary algebra class, where you're supposed to calculate how many nickels you've got in your pocket, and if you run through the equation and it comes down to x equals 1 divided by 1/4, you don't call that the answer. I mean, nobody goes around saying, oh, I've got 1 divided by 1/4 nickels in my pocket. Normal people call that 4, okay? And, well, the way to clean it up as far as how the algebra goes is if you've got 1 divided by 1/4, well, you can multiply that by 4 over 4, because that's a form of the number 1, and you can multiply by 1 without changing the value of something. So this will still be equal to what you started with. And the reason you want to do that is down here in the denominator, 4 divided by 4 cancels out. So 1 divided by 1/4 is better known as 4. Well, just as you don't leave fractions within fractions when you're writing down numbers, it is also not exactly wrong, but unconventional to leave fractions within fractions with units. And it's kind of a similar thing you would do to clean them up. That says units, by the way. I'm old, so I write in cursive, and you're just going to have to deal with that. I usually read it out loud anyhow. If you can't read my writing, you should hear me telling you what I wrote. Once again, just like I did up here, multiply by a factor where the top equals the bottom, this time with units in it instead of numbers. Seconds divided by seconds, that's just like multiplying by 1. And the reason for doing it is the same as before. Seconds over seconds cancels out up in the numerator, leaving you with just meters. And down in the bottom, seconds times seconds can be more compactly written as seconds squared. And so the way this would usually be written is 9.8 meters per second squared. Now, if you're sitting out there trying to picture a square second, you know, it's like, well, I don't get it. You know, a square inch is about that big and a square foot is about that much, but square second? Yeah, the problem is you shouldn't be trying to picture a square second in the first place. What it means is what we started with in the first place, okay? It means meters per second per second. It's telling you the rate at which this rock is gaining speed. After 1 second, its speed is 9.8. After 2 seconds, its speed is 19.6. After 3 seconds, it's 29.4, and so on. Every second, it gains another 9.8 meters per second, 9.8 meters per second, okay? So what we had in the first place is what it means, but this is just kind of a shorthand way of writing that. Okay, this is equivalent to that, and this is how most people are in the habit of writing it. Okay, what's next on the script here? Oh yeah, this number here, you're going to see that number a lot before the course is over. That is the acceleration of any freely falling object. I don't care if it's big or small. I don't care if it's dense or fluffy. I don't quite care if it's square or round. Any freely falling object near the surface of the Earth picks up speed at the same rate if you drop it. Now, you may be, that's in the notes right there. Any 4-year-old can tell you that if they drop a rock in a leaf, the rock gets to the ground first. But the reason for that is that the leaf is not a freely falling object. Freely as in free of influences other than gravity. The reason the rock falls more slowly is because air drag has a greater influence on the leaf than on the rock. The rock is pretty heavy for its size, so at least at low speeds, it's pretty effective at plowing through the atmosphere without much effect from the air drag. The leaf, on the other hand, weighs so little that even a small amount of air drag is significant compared to its weight, and it holds it back. So what I usually do at this point is when I'm teaching this at, on campus, is I've got a plastic tube, a clear plastic tube that you can see inside of, and in it there's a penny and a feather. And I can drop them both at the same time if I just take that tube and quickly turn it upside down, and the penny and the feather will both drop. And when I do it the first time, the penny goes plop, and the feather kind of goes fluff, 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 and takes its sweet time reaching the bottom of the tube. And then I say, I will now eliminate the air drag by eliminating the air. And I hook it up to a vacuum pump and pump on it for a few moments. And after I'm done, when I do the same thing over again, yeah, if you're looking closely, the penny still falls a little faster than the feather because, first of all, I didn't pump on it for very long, and I didn't get a good hard vacuum. There's still a little bit of air left. Furthermore, the feather rubs a little bit against the inside of the plastic tube, and there's a little bit of drag from that, and probably a little bit of an effect from static electricity as it rubs on it. And anyhow, it stays pretty close to the penny. A better version of the same demonstration that I would encourage you to look at, since we're all doing this at home, and I don't have my vacuum pump or anything here with me, is if you go into YouTube, one of the many videos that's in YouTube is of the Apollo astronauts in the early 1970s. They took, one of them took a feather, and I think the other thing he had was a hammer, up to the moon, where there is no air. I mean, it's a better vacuum than you're going to get in any laboratory here on Earth. And dropped them both at the same time. And the hammer and the feather, they just stay right next to each other all the way down to the ground. Just put something about free fall on the moon or something like that in the search box, and you should be able to find it pretty easily. Or if it gives you any trouble, just ask me and I can send you the link. But to the extent something is a freely falling object, it will accelerate at this rate, 9.8 meters per second squared, which are the units we will just about always use in this course. Or if you're old school and want to measure things in feet instead of meters, it's about 32.2. Anything, if you drop it from high enough, begins to lose acceleration, okay? If you drop something out of an airplane, it's a freely falling object. If it's something, you know, like a lead ball or something like that, or even a rock, it'll be a freely falling object for the first few seconds. But the thing is, air drag is a velocity-dependent force. The faster something moves, the larger the friction force on it becomes. And so as a falling object goes faster and faster, the friction becomes greater and greater. And after a few seconds, the air drag will be a few seconds or less if it's a leaf. Air drag will become significant, and the acceleration starts to taper off until after a while, it's no longer gaining speed at all. A skydiver reaches a terminal velocity of, I think it's somewhere around 120 miles an hour, give or take, depending on whether they've got their arms stuck out or they're curled up in a cannonball or whatever. But for the first few seconds after you drop something that's heavy for its size, this would be the rate that it gains speed. If it doesn't fall too far, you can ignore air drag all the way down. So let's turn our attention to a special case. Uniformly accelerated motion, meaning that the acceleration is constant. One example would be a freely falling object. There are other cases where something's acceleration does not change with time. It can be shown that if something has a constant acceleration, meaning that it gains speed at a steady rate, this little group of 5 equations applies, and you will find them on your formula sheet. I thought I had the formula sheet here somewhere, but I don't want to take the time to dig around in the papers. That formula sheet that you can use when there's a quiz or an exam. This is the kind of thing it's for. So you don't have to memorize all these equations. It's right there where you can refer to them. So I'm going to run through a couple of examples, and then I'll have some examples for you to work on. And that's going to be what's left of section 1. Now, what I like to do, you know, it's a 3-hour class. If I lecture about physics for 3 hours straight, they're probably going to have to carry people out of the room in stretchers at the end of that. So I like to put a 10-minute break in the middle of the class. And we might not be dead center in the middle of this little lecture that I'm giving you yet, but it's getting fairly close. And considering that a lot of the second half of the class is going to be me telling you to pause it, um, I think we're probably well past the middle of the recording that I'm going to make for section 1. So what I'm typically going to do, and that's what I'm going to do today, is instead of just one 3-hour, 2 or 3 hour recording, I'm gonna break the recording where we would take the 10-minute break in the middle of the class. So you should in Blackboard find another recording right below this one that says something like section 1 continued or section 1 part 2 or something like that. And the rest of today's class will be that recording there, just to keep down, minimize the hugeness of each file here. So see you on the other side of the, well, no, I won't see you, but you'll see me, or at least hear me on the other side of the break.